Welcome to this session. This session, we want to get eigenvalues and eigenvectors of a matrix which is non-symmetric, and we'll find out that for this non-symmetric matrix, all the eigenvalues are distinct, and then after getting the eigenvalues, we'll find eigenvectors. So, solution. So the first step is to get the eigenvalues. And eigenvalues, you solve the equation A minus lambda I equals to 0. So this being a 3 by 3 matrix, we pick identity matrix of order 3 by 3. So we'll have the determinant 3 minus lambda 1, 4, 0, 2 minus lambda 6, 0, 0, 5 minus lambda equals to 0. Now, this being a triangular matrix, to get the determinant, we simply multiply elements along the main diagonal. So it will be 3 minus lambda times 2 minus lambda times 5 minus lambda equals to 0. So which means lambda 1 equals to 2, lambda 2 equals to 3, and lambda 3 equals to 5. And actually, this is generally true that for any given triangular matrix, eigenvalues are simply the elements along the main diagonal. So even without writing the characteristic equation, when you see the matrix 3, 1, 4, 0, 2, 6, 0, 0, 5, because this is a triangular matrix, and to be specific, an upper triangular matrix, then to give eigenvalues of this matrix, you don't have to do any calculation. They are simply pick the elements along the main diagonal. So 3, just to keep that order, we can say this is 3, and then lambda 2 is 2, and then 5. But anyway, there's nothing special in that order, but can just order them this way. So after getting the eigenvalues, next task is to find eigenvectors. And to get eigenvectors, you remember the eigenvalue-eigenvector relation. So eigenvectors. So you find eigenvector for each of the eigenvalue you have solved. So lambda 1 equals to 3. So let eigenvector be U1. Now, because we are dealing with a 3 by 3 matrix, so this is the structure of the eigenvalue. So the matrix this is the eigenvalue eigenvector equation that we need to solve for this vector U. So we write A matrix is 3, 1, 4, 0, 2, 6, 0, 0, 5. You multiply by U1, U2, U3 is equals to lambda is 3, and then vector is U1, U2, U3. Then you use your linear algebra knowledge to solve this equation. Now you see this is the same as writing 3U1 plus 4 plus 1 u2 plus 4u3, and then u2 plus 6u3, and then we have 5u3 is equals to 3u1, 3u2, 3u3. And then for this equality to make sense, that means that the first line, 3u1 plus u2 plus 4u3 should be 3u1, and then 2u2 plus 6u3 should be 3u2, and 5u3 should be the same as 3u3. So from this equation, we have u2 is equals to minus 4u3. And then from this equation, you take 3u2 to the left-hand side. So you have u2 is equals to minus 6u3. And this one tells you that 2u3 is equals to 0. So then now, from this equation, it implies that u3 equals to 0, and u2 is also 0, because if you get u3 to be 0, replacing 0 here, you get u2 is 0, or replacing 0 here, you get u2 is also 0. Now, we let u1 to be any real number, t, such that this t is non-zero, because if it is 0, then we'll have 0, 0, 0, and by definition of an eigenvector, we can't have a 0 eigenvector. So therefore, u1 vector is u1, u2, u3, given by u1 is t, u2 is 0, u3 is 0, which can be written as 1, 0, 0, t, and t is any non-zero real number. So letting t to be 1, then u1 will be the vector 1, 0, 0. Now, since the eigenvectors are not unique, then the general eigenvector for u1 can just be written as u1 is t 1, 0, 0, and we specify t, so say odd, t is non-zero real number. So any value of t you put here will give you a corresponding eigenvector for lambda equals to 3. And then second, lambda equals lambda 2. Lambda 2 is 2. So we have the matrix. We have to solve this equation. u2 equals to lambda 2 u2. So we'll have 3, 1, 4, 0, 2, 6, 0, 0, 6. So let u2 be x1, x2, x3, or you can still use u1, u2, u3. 2, x1, x2, x3. So from this equation, we need to solve for x1 up to x3. So we'll have 3x1 plus x2 plus 4x3. And then we have 2x1, x2 plus 6x3. And then 6x3. No, this is not 6. This is 5x3. This should give us 2x1, 2x2, 2x3. And for this equation to make sense, then 3x1 plus x2 plus 4x3 should give us 2x1, and then 2x2 plus 6x3 should give us 2x2, and then 5x3 should be the same as 2x3. I think it should be clear that this means 3x3 equals to 0, which implies x3 is 0. From this one, 6x3 is 0, which still confirms that x3 is 0. And then here we have x1 equals to minus x2 minus 4x3. And since x3 is 0, so it means x1 equals to negative x2. So then now we say, let x2 to be t, where t is any non-zero real number. Then this implies, since x1 is minus x2, x1 will be minus t. And then you say your eigenvector u2, u2, which is given by x1, x2, x3, will be, where there's x1 you put minus t, where there's x2 you put t, where there's x3 you put 0, because that's what we have solved. So this is the same thing as saying minus 1, 1, 0, and then you multiply by t. T is a non-zero scalar. So we can have this as our u2 vector, or we say, when I say t to be -1, then u2 is given by 1, -1, 0. Or you can say, when I say t equals to 1, then u2 is -1, 1, 0. Or you can just write u2 is that vector 1, -1, 1, 0 times t, or you can write it as u2 is 1, -1, 0, and then times a real number t, or even k. So where this t is any non-zero real numbers. Remember, eigenvectors are not unique. So that's why I'm saying that we can fix, you see, if you fix t to be -1, you get a different thing. T for 1, you get a different thing, but all of them are okay. And lastly, lambda 3 equals to 5. So we need to have a u3 equals to lambda 3 u3, So our matrix A is 3, 1, 4, 0, 2, 6, 0, 0, 5. We multiply by vector 3, U3, which is, you can write x1, x2, x3 equals to 5, x1, x2, x3. And so we'll have 3x1 plus x2 plus 4x3, 2x2 plus 6x3, 5x3 equals to 5x1, 5x2, 5x3, and then next, this implies that 3x1 plus x2 plus 4x3 equals to 5x1, and 2x2 plus 6x3 equals to 5x2, and 5x3 equals to 5x3. So this equation is always true for any value of x3. And then here, this means that 3x2 is the same as 6x3. Take 2x2 to the right-hand side. So it's the same thing as saying x2 is the same as 2x3 divided through by 3. And then this one implies, or is the same as, you say x2 is equals to, so 2x1 minus 4x3. So since x3 is given by, x2 is the same as 2x3, then you can write 2x3 equals to 2x1 minus 4x3. So bring this to the left-hand side, we have 6x3 equals to 2x1, and that means x1 divided through by 2 is 3x3. So all these variables are expressed in terms of x3, and x3 can take on any number from this equation. Any value, any real number you pick will satisfy this equation. So you say let x3 be any real number t. Of course, should not allow all of it to be 0 because it will result into a 0 vector. Then this implies that x1 will be 3t and x2 will be given by, since x2 is 2x3, so this will be 2t. So that our vector u3 is x1, x2, x3. So where there's x1, you put 3t. Where there's x2, you put 2t. Where there's x3, you put t. So factor out t. So 3, 2, 1, and then t. This t is any non-zero real number. So therefore, u3 is given by 3, 2, 1 times t where T is any non-zero real number, or simply U3 is given by 3, 2, 1 by taking T equals to 1. So that's how we find eigenvalues and eigenvectors for that matrix. Thank you.